Now that we've talked about derivatives and learned a little bit about how to deal with them and calculate them, we're going to start to use them and start looking at different behaviors and functions. All of these things start becoming a little bit more abstract, but they're more of an, say, an introduction into the higher order of thinking that calculus kind of implies. And so we want to talk now about some applications. And the first thing we got to do is, as with everything, whenever you're learning something new, you got to start defining things. So let's define what an extrema is. And there are different types, but in the general sense. Let f be a function, and let it be defined on an interval I containing c. Now, if the function value at c, okay, that's this, the function value at c is a minimum of f in I, or if you want to check that it is, then it has to be less than or equal to all other values, all other function values in that same interval. That's kind of a mouthful, so let me go back and read that again. The function value at that point C is a minimum of the function in that interval if that function value at C is less than or equal to all other function values within that interval. Okay, it's a maximum if it's greater than all other function values in that interval. And these are known as absolute mins or maxes. All right, that's also what they're called. But as you can see, these are just in general in extrema. This is specific. You call that based on whether it is a min or a max. All right, now it does not say anything about this interval. The definitions are kind of funky that way. They don't actually tell you anything other than this is what it is. It doesn't tell you necessarily how to use it, how to find it, and how to perhaps to distinguish it. But if we excuse me, if we happen to look at an example quick, so that you have a function here, and it's just kind of, it starts down here, kind of comes down and kind of comes up and kind of comes over here and ends. Okay, so we have this interval. Now by inspection, you can say, okay, well here's a low point, so this is a minimum or an absolute minimum. Okay, and then by inspection again, you can say, well that point right there, that end point is an absolute maximum. All right, and so, and that's fine, that's all it's saying in this definition. I can just identify it because I can see that, okay, that's higher than any other y value in that function, and this is lower than any other y value in the function, therefore it's a maximum and a minimum. Okay, fine. Now let's change it up slightly. And when I mean slightly, I mean very slightly. And then we'll take a look at what happens. So we have the same function, except this time we don't have solid endpoints. Actually, I'm going to keep that one there. Okay. So now it doesn't really look that different, except there's a problem. By examination, we can see that we still have this absolute minimum. But now this point right here is not a maximum because I have a point over here that's higher. I have a point over here that's higher yet. I have a point over here that's higher yet. And I can continue this process until I get very, very, very close to that endpoint, except that endpoint doesn't exist. Okay? And so the problem here is that endpoint is the maximum. However, in our definition, they kind of set it up on an interval containing C. C is that point right there. The problem is our interval doesn't contain it. And so there's no way to express that point. And whenever you find a point, I can find one closer. And it just continues on and continues on and continues on. And so there's a lot implied in this definition. So unfortunately, in the second example, we don't have a maximum. It just doesn't exist because it cannot satisfy the conditions of the definition. All right, there's no limit taking necessarily here. So just be aware of that. Okay, by the way, the same thing can happen with the minimums as well. It's not restricted. The definition of relative extrema, and in your book you'll notice that the extreme value theorem kind of separates these two. I'm skipping that. I'm just going to concentrate on definitions right now. We'll hit the extreme value theorem later. But number one, if there is an open interval, so now at least we have some kind of an idea here. We are dealing with an open interval now, containing C, on which f of C is a maximum, then f of C is called a relative maximum of f. Or you can say that f has a relative maximum at C, comma, f of C. Okay, so now going back to what we had here, now we still have a problem here because we have an open spot here where that's the maximum. Again, in the first one over on the left, we have our absolute minimum and our absolute maximum. Okay, now if we were to create an open interval version of that, and so I'm just going to simply kind of copy that down here. So now I have an open interval. This, and we're defined at C, okay? So containing C, so here's a C. Then this is a relative minimum. We say relative because, well, we don't know what the endpoint's going to be. So we don't know if the endpoint is going to be less than or equal to, or we just don't know because it's an open interval. And so we're going to call it a relative minimum. There is no relative maximum in this case. Okay. And so this kind of leads us into something, and something that we have talked about before a little bit, but it leads us into this idea that at some point, perhaps, whenever you see a curve and it goes from sloping down to curving and then sloping up, then you might ask yourself, well, if that's, as long as it's contained within that interval, we get a relative minimum. Or in the case of a reversed, we get a relative maximum. So what's so special about that point? All right, so that's all this is saying. This particular definition is just defining that open interval containing C. So now we're talking about open intervals. And now we can have relative mins or maxes. On a side note, and it's not typically in a 100 or 200 level calc class. Excuse me. But there exists something called a global maximum or global minimum. And so what you can have is perhaps, say, on a parabola, when you hit that vertex, that is a global minimum or maximum. There is no other point that exists on that function that is higher or lower than that point in the entire negative infinity to infinity interval. So there's no real number that's higher or lower for that function. And so that's called a global minimum or maximum. Not really too concerning here, but going back to this, we see that every time we hit a low spot or a high spot that's on a curve, we get a special point that's usually a minimum or maximum. And that leads us to a third thing. We're talking about the critical number. So let f be defined at C. So our function is defined at whatever C value. If the derivative at C is 0, okay? If the value of the derivative at C is 0, or if f is not differentiable at C, then we call C a critical number of f. Sometimes this is known as a critical value. Number and value are kind of synonymous with each other. And so if we take a quick look at an example here, and I'm going to do a graphical and I'll do a little bit of an analytical example. We've got this, and notice there is no requirement here of an interval. It doesn't have to be open or closed. So I'm simply going to just make a function here, and I'm going to make a parabola. Okay. All right, so now I want to know where the function has a derivative of 0 or whether or not it's not differentiable at c. Okay, so now where is it 0? So what value makes it 0? Well, as we look, here is one slope. Okay, here's another slope, and they're getting a little bit less and a little bit less. Once we hit the very bottom, we have a horizontal slope. This is where our f prime of x is equal to 0. And so what we'd like is that point right there. And so we call that singular point f of c because it's a special point. Okay. So now let's take a look at a more analytical version of it. And so we can take, for example, f of x is equal to x squared minus 2x plus 3. Well, in that case, then our derivative of x is equal to 2x minus 2, and we want to check to see where that's 0, because wherever the derivative is 0, then we have a critical point. Okay, so we add 2 to both sides. We get 2 is equal to 2x, or 1 is equal to x. All right, so now we have our c value. I know it says x, but it's still c. Don't worry about it. It's a single number. Okay, and so now we have our c value. That is the value at which the derivative is 0, and therefore 1 is a critical number of our function. For the second portion of this, and then we're going to let it be done. For the second portion of this, it says what if it's a critical number if the derivative is 0 or if f is not differentiable at c. And we've seen some examples of this. You have perhaps a line coming down, all of a sudden sharp turn, and it turns into, say, the square root. Okay. At that point, this point is called a cusp. And we've learned that in absolute values, that cusp is a point where where no derivative exists because the one-sided limits don't agree. One-sided limit is negative, one-sided limit is positive. And so this is not differentiable, which means it's a critical point. Okay, so that's something that we have to look at. Other critical points are, of course, jump discontinuities. So if you're talking about a hole, or if you're talking about a step function where it steps up, then you have a discontinuity there, and you're not going to be able to get a derivative. Okay, we kind of learned that before, and so then the other one is if you have a vertical asymptote, okay, then you're going to have a problem at that vertical asymptote because you're dividing by 0 and you can't do that. And so that wherever that vertical asymptote lies, there's another critical number. Critical numbers are going to play a fairly important part in your testing of the extremums. And so we want to make sure that we identify all the critical numbers in our problems.